This is actually a joint work with my colleague Reza Shokri at Cornell Tech. And what we propose in this work is a generative framework to synthesize location trajectories that are plausible but also preserve privacy. So if we look at the general problem of data publishing, we have that on the one hand, companies have an increasingly large amount of data about us. And so it would be beneficial for researchers to be able to get access to that data. On the other hand, this data is often sensitive, which means that because of privacy concerns, researchers often cannot get access to such data sets. So the question we ask in this work is, can synthetic data help here? We'll focus specifically on location data, but the basic question is, can we actually share a synthetic data set instead of the original sensitive data set? So the general task we have is data synthesis. What we're looking at is this problem of trying to transform real sensitive data into a synthetic version of it, which is similar but not the same. We may try to do this, for example, with a generative model. And so as such, the goal here is to preserve the data format and the statistical properties of the original data. So as an example, this has been done by the US Census Bureau, and they have this longitudinal business database, which they have created a synthetic version of it. And in fact, researchers can get access to this synthetic database. So why use synthetic data as opposed to other approaches? Well, for one thing, synthetic data has the same format as the real data, which means we can use existing code and applications without changing them. It can also allow us to save time, even if we're ultimately trying to get access to the real data set. Perhaps we have to sign a data use agreement, and this will be a long process. And the way this works is, if the data owner can send us a synthetic version of the data, we can then immediately start with the development and software testing, etc. It's useful in various scenarios. You can think of it as perhaps in education. If you're trying to teach students how to use statistical packages such as R, you might consider giving them synthetic data. I'll give you an example also that in some cases, synthetics can preserve privacy in a way that cannot quite be replicated by other techniques. So now let's focus on location data for the rest of the talk. The general goal that we'll have is generate synthetic location traces and release them instead of the original data. But I'll now give you an example of a particular application domain for location-based services. So for example, I can use location-based service to find restaurants nearby. Now, when I do this, my location is sent to the location-based service, and then I get a list of restaurants which hopefully are within walking distance. Now, if I want privacy in this scenario, I could, of course, do something like add noise to this location before I send it to the LBS. But in this case, what I'm actually doing is I'm degrading the quality of service I'm receiving, because now I might get some restaurant recommendations which are not within walking distance. Now, if I do have synthetic location trajectory, on the other hand, I can do the following. I can share with the location-based service a mix of fake locations and my real location. In this way, once I get the result back, I can locally filter out the results that are not relevant to my real locations. And therefore, even though I pay an additional bandwidth cost, I will not have degraded the service that I'm getting. I will get the same reply as if I had only shared my real location. Now, the idea here is that if I do this, then, and the fakes that I'm using are plausible, then they can confuse the adversary, and therefore I get some location privacy. So you can ask, OK, why not use existing techniques to really sanitize location trajectories? Well, you can think of doing things like anonymization, but this has been shown not to be sufficient for location privacy in several papers. There are heuristics, of course, to generate synthetic location traces, but what's really important is that we preserve utility and that we actually generate synthetics that are plausible, that is realistic trajectories. Because if not, in for example, the location-based scenario, then the adversary can simply filter out those fake trajectories. We could try to go the differential privacy route, but unfortunately, these do not produce full traces, except for the exponential mechanism. Now, the exponential mechanism, the way it works is it assigns a score to each possible output record. In our case, an output record is a synthetic trace. And then it samples from the resulting probability distribution. Now, in our case, if we have R location and T timestamps, there are R to the T possible location trajectories. Therefore, it's simply infeasible to sample from this space. So what can we do instead? We propose to have a generative framework with 2 steps. In the first step, we focus on constructing a utility-preserving generative model. This is a data science task. In the second step, we will take the synthetic location traces we have generated in the first step and now only release them if they pass a privacy test. This is how we ensure privacy. So concretely, we start with a set of sensitive location trajectory as input. We randomly select a subset of these. We'll call these the seeds. And from these seeds, we use a generative model to sample synthetic location trajectories. Okay? From these sampled trajectories, to safeguard privacy, we run the privacy test. And whichever samples do not pass the privacy test, we simply throw away. We discard them. And we release the rest. So how can we actually do this? Well, we need to be able to model human mobility to construct this utility-preserving generative model. And our main operating premise in this work is that the main features of human mobility can actually be split between a set of geographic features. These have to do with the trajectory of the user, where specifically the user goes. You can think of GPS coordinates, and the semantic features. The semantic features have to do with the semantic of the location. Is this location the user's home? Is it his workplace? Is it a coffee shop? With this, we can actually propose 2 metrics, a geographic similarity metric and a semantic similarity metric. Now, on the one hand, we do expect that most people are going to have low geographic similarity, because if we take 2 random individuals, they're going to visit very different locations during their day. On the other hand, most people are expected to have high semantic similarity, because individuals have similar lifestyle. People are at home during the night. During the day, they go to work. Perhaps the opposite if they're a grad student working on a deadline. But the key observation here is that to construct a generative model, we will take the geographic features, and they are sensitive. Therefore, this is the information that must be protected. On the other hand, the semantic features are useful, and therefore they must be preserved. So to do this, we start by automatically grouping locations with similar semantics. What that means is we're going to end up with classes of locations, maybe 1 class for the homes location, 1 class for the work location, 1 class for maybe the shopping centers. And with this, we can now produce a synthetic trace starting from a seed trace by converting the seed trace into a semantically similar, yet geographically different synthetic trace. So the idea here is we want to discard the geographic features because these are sensitive. But we want to keep the semantic features the same because these are useful. So concretely, here's how it's going to go. We're going to start with a seed trace. And you can think of this seed trace as being in the geographic domain. We're going to transform it into the semantic domain to get the semantic seed trace. We will do this using the location semantic classes that we have. Specifically, we will replace each location in the seed trace with the label of the semantic class in which that location falls. So now you can think of this as getting a color trace where each color essentially represents a semantic class. So there might be 1 color for the homes location, 1 color for the workplaces, 1 color for the shopping centers, etc. Now that we have the semantic seed trace, we actually need to reconstruct, in some sense, the geographic information. So what we want to do is we want to sample back a plausible geographic trace given this semantic trace. To do this, we'll do the following. We will cast this problem as a hidden Markov model decoding problem. Basically, we will pretend that we have observed the semantic seed trace and ask the algorithm to give us a plausible trace through the locations which explain the observed semantic information. OK, so this is the generative model. How do we actually go about ensuring privacy? Well, the first thing is, what are we worried about? What we are worried about here is what is the synthetic trace actually going to leak about the seed trace it came from, right? So we're going to release the synthetic trace if it passes the privacy test, but the seed trace is what was sensitive. So what we want to make sure of is that because the synthetic trace came from the seed trace, it does not leak information about it. So we will do this using 2 tests. we will try to have the first test protect against an adversary that is trying to infer the locations visited in the seed. The idea here is that we want to ensure that the synthetic trace and the seed trace are sufficiently geographically dissimilar. Basically, in the generative model, we do discard the geographic information from the seed trace. But it's possible, it could be that we're unlucky, or it could be that there is something weird about that seed trace, which might mean that we produce a synthetic trace with significant geographic overlap. And so this is what we want to prevent here. The second privacy test is going to be aimed at mitigating membership disclosure. The idea is we want to prevent an adversary who is looking at the synthetic trace from deducing something about the input trace which could have been or must have been its seed. So what you don't want to have is you don't want to have an adversary that's looking at this synthetic trace and say, it must have been that this particular input trace was the seed that it came from. So to do this, we'll use the notion of plausible deniability. The idea is the following. Let's ensure that we can find at least n alternative traces which are not part of our seeds, from which we have not generated any synthetic trace, which could have plausibly produced that synthetic trace if it had been the seed. So again, here, if we can find enough of these, then we release the synthetic trace. So when we actually go and run this generator that we have on a real data set of location trajectory, you can ask, OK, what kind of utility is going to be preserved in the synthetics? Now, we take a very detailed look at this question in the paper, but I just want to give you two examples. You can ask, for example, is the distribution of semantic similarity among the input trajectory preserved? Now, this is important because I was just arguing a moment ago that the semantic information is actually what's useful, and therefore that's what we want to preserve. As shown by this QQ plot, we can see that this is the case. So if we take two random real traces and look at their semantic similarity, the distribution of which is very close to the distribution of the semantic similarity of two random synthetic traces. Now, as it turns out, we also preserve some geographic features. So for example, we preserve the proportion of visits for the top 50 most visited location. OK. So now these privacy tests that we have help us ensure privacy in the scenario in which we are releasing synthetic location trajectories. But if you remember, in the location-based services scenario that I told you about before, what we're actually doing is we are sharing with the location-based service a mix of fake and real locations. So in this case, what's actually important in addition to the privacy test is to ensure that an adversary cannot simply filter out the fake locations to find out the real location of the user. Because if an adversary can do so, then we have no privacy. OK. So now, as it turns out, in the last decade, there have been many proposals on how to create fake locations. And this is because these fake locations are a major defense mechanism for location privacy. So what we did is we ran a state-of-the-art inference attack to compare the privacy that we get using these other techniques that have been proposed versus using our synthetic location trajectories. And here, the location privacy of the user is what we want to maximize, and it is going to be equal to the inference error of the adversary trying to locate the user. And as we can see in the graph, our method significantly outperforms these other techniques. So to sum up, what we have done is propose a generative model which works by decomposing mobility into its geographic dimension and its semantic dimension. Based on this generative model, we have proposed a generative framework which ensures privacy using privacy tests. And in particular, it uses this notion of plausible deniability. And finally, I just want to mention that we have open sourced our generator tool, which you can find at this address or from my website. I am the contact person for the tool, so if you end up using it and need assistance, please feel free to email me. Thank you.
Hi, thanks for the talk. So is the model that the LBS just gets where you are now in both your real trace and 10 or 20 fake traces, or does it see all the whole traces?
It sees whenever the user is actually querying the LBS.
But
so,
the user's device
yeah,
keeps
the user's
track
device.
of where my 20 fake friends, 20 fake me's
yes.
are.
So what happens is that we take a bunch of fake traces before anything is happening. And then the first time that the user queries the LBS, we share the real location, and then whatever location was visited at that time in these synthetic or fake traces.
But don't
and then
you
we
need
continue
to know
doing
where the user's going to be in order to generate the fake traces?
No, because we need to know the general area, right? There is a map and you have some number of locations. But we don't actually need to predict into the future because we can generate the synthetic traces ahead of time.
From the
and
seed,
then use them. From a bunch of volunteers that have contributed their traces, which some of them may end up as seeds.
Sorry, I just want one more thing.
Sure, go ahead.
But then don't you have an auxiliary data problem? Like if the LBS happens to learn for sure that you were in a particular place at a particular time, they can then figure out which traces were real and which traces were fake.
So this is kind of what we're trying to prevent. But in the scenario that you described where the LBS or the adversary in general actually knows something more, this is just modeled by increasing the background knowledge of the adversary.
Right.
So the results I've shown is for one particular background knowledge. And the general answer is that, of course, if you increase the amount of background knowledge the adversary has, your privacy will decrease. But what we're interested here is not in the absolute privacy that you get, but in how our techniques compare relatively to other techniques. So if you have such a scenario where you increase the amount of background knowledge of the adversary, you will see all techniques decrease in the location privacy they provide, but it should be that the order is preserved.
Okay. Let's move to the next question.
Hi.
Yes.
Thanks a lot for your talk. My question is, have you considered that the location, the LBS services might actually affect the real user's behavior, and therefore they would, for example, I could suggest you go to a restaurant, then I see in the next step, if you went there, then I know that that's the real one. So I suggest 10 restaurants, only one of your traces goes to the one that I suggested.
Well, we're not explicitly modeling that case, but the thing is that the semantics are preserved and the synthetic traces are semantically similar to the original traces. So what that means is that suppose that you go to a restaurant at some point and then you go to some other semantic location, then it's likely that in one of the fake that you're using, you will visit some other location which has the same semantic class. So it might also be a restaurant, and it might also be among the possibilities of what was proposed for the query to that location. Yeah.
Nice work, Yingzhi from Lehigh. So I have a question is, have you considered about movement speed of the person? For example, like in the synthetic data, maybe the restaurant is too far from home, and that person cannot catch the restaurant in a reasonable amount of time.
Yeah, so we are dealing with this. It's one of the things that you have to, I have not explained, but that you have to actually deal with. Basically what we do is that when I say we are preserving the semantic information, we're preserving the semantic information, but we're allowing flexibility so that you can actually generate, let's say, if I rephrase the question, let's say that you are going to work within walking distance. It takes you 5 minutes to get to work. You would like a seed trace like this to be able to generate a trace where the commute is much longer. And we can support that by essentially allowing some flexibility in how the semantic information is preserved.
Hi. Brian Rosenberg, Qualcomm. I'm worried about semantic confusion. So, one person's workplace is another person's home in a mixed-use kind of development, and for a school, there's kids who go there who it's their school, but the teachers are employed there, and so don't the sort of semantic categories give you some information about the person, or?
For the leakage of information, not really, because it's prevented by the plausible deniability privacy test. But it is possible that a location would have some semantic for one individual and then some other semantic for another individual. But this is not a problem in our case.